Good morning, everybody. We are now looking at section 2.12. I believe, if I'm not mistaken, we have 3 more sets of notes, and then it's going to be time to start getting ready for our next test. As I've mentioned before, we do have a lot of ground to cover before we can really call this class finished, and the spring break did not help us. The coronavirus has not helped us, and there's going to be a lot of things we're going to have to consider before the end of the semester. Today we're going to look at estimating a population mean, and a lot of times what we encounter with data is our mean is based upon a sample. It's not based upon the entire population. For example, if we were to survey the entire student body at Perry Central, that is a distinct possibility. It is something that can be done. We could actually go through and conduct whatever research we were doing with all, say, 900 students that are within that school building. However, if we were to conduct the same study, and this time perhaps we're looking at just the population of the state of Kentucky, it would be really impractical to want to survey or research every individual within the state. So what we want to do is we will take samples, and based upon those samples, we will make predictions about the entire population as a whole. This has been kind of the foundation of what we started talking about at the very beginning of this class, right from the start, when we first started talking about samples. With what we're looking at now, we're going to actually try to determine, can we come up with an accurate range for, say, the population mean based off of sample information. And that's what we're going to start off with right here when we get into the first example on this set of notes. So you can see what you're looking at right now on the screen. A very common problem in statistics is to obtain information about the mean of a population. Maybe you want to know the mean age of people in the civilian labor force, the mean cost of a wedding, the mean gas mileage of a new car, or the mean starting salary of liberal arts graduates. If the population is small, you can normally determine mu, or the mean, by taking the population data. If the population is large, just like we were talking about with the state of Kentucky, that is often not very feasible, so we have to gather information from the samples about the population itself. So one way that we obtain information about a population without taking a census is to estimate it by using the sample mean, which remember is X bar. And we're going to see that here in our first example. We have the U.S. Census Bureau publishes annual prices for mobile homes and manufactured housing statistics. The figures are obtained from samples, not from a census. A simple random sample of 36 new mobile homes yields the following prices in the table that you see, and these prices are in thousands of dollars. So it says use the data to estimate the population mean price of all new mobile homes. I've gone ahead and I've taken that data and I've entered it into a Google document or Google sheet. So column A are my sample prices from the table that we were given. This sum represents the value of the sum of all the sample prices, and then the sample mean is just the sum divided by 36 because we had 36 samples within that given problem. So our sample mean is 63.28. So based upon this information, we can estimate that the mean price of all new mobile homes in the United States is right around $63,280 based upon just the sample that we have. Now this data that we're looking at is what we refer to in statistics as a point estimate. A point estimate, you can see the definition here in the green box, is a value of a statistic used to estimate the parameter. Remember, the parameter is the population value, statistic is a sample value. So we're using the statistic to estimate the parameter for the entire population. When we talk about this, we also want to know how accurate is the sample mean as it relates to the population mean. And so that's where we come up with what we call a confidence interval estimate. So a sample mean obviously is not always going to be equal to the population mean. It will sometimes be fairly close, but sometimes it might be really way off from the population mean, and that can be due to sampling errors within the given samples that we might be looking at. So therefore, we want to accompany any point estimate with what we call the confidence interval estimate. So we're going to introduce that by example. Example 2 is asking us to once again consider the mean price, or actually estimating the mean price of all new mobile homes by using the sample data from example 1. So we want to assume that the population standard deviation of all such prices is $7,200. Now, in the context of this problem, we want to refer to 7,200 as 7.2. So that's going to be our sigma. And it just simply says for part A to identify the distribution of the variable x bar, that is the sampling distribution of the sample mean for samples of size 36. So for part A, recall from our last set of notes that mu sub x bar is equal to mu. But in this case, we do not know what mu is. That's what we're trying to estimate. We do know, however, that sigma sub x bar, remember, is equal to sigma divided by the square root of n. So in this case, we have 7.2 divided by the square root of 36, which is going to be equal to 1.2. So our sigma sub x bar is 1.2. And the last thing that we really want to determine is the identify the distribution. That's what it's asking us to do in part A. Well, one thing that we know is that this is normally distributed. And the reason we can say that is because our sample size is 36. Remember, in the previous notes, we looked at as long as the sample size is 30 or greater, we can say that it is normally distributed based on the sample means. For part B, it just says to use part A to show that 95.44% of all samples of 36 new mobile homes have the property that the interval from x bar minus 2.4 to x bar plus 2.4 contains mu. What this means is, if you recall when we talked about the 3 standard deviation rule for a normal distribution, 95.44% of all data lies within 2 standard deviations of the mean. So for part B, what we're talking about with this one is, again, we don't know what mu is. So let me just sketch what we're talking about here. There's our normal distribution curve. And we're looking at 2 standard deviations to the left and right of that mean is going to give us the 95.4% confidence interval. What this question here is asking us to do is just to show what that interval might consist of. So even though we don't know what mu is, what we do know is our sample standard deviation. So our sample standard deviation, x bar, is 63.28. We calculated that in part 1, or example 1. So to find the 95% confidence interval, this range of values that our true mean might lie within, for the left bound, it's going to be 63.28 minus 2 times our standard deviation, which is 1.2. And then the upper bound on the right-hand side is going to be 63.28 plus 2 times our standard deviation, which is 1.2. So when we simplify both of these, what we end up with is 60.88 and 65.68. So our confidence interval is between 60.88 and 65.68. What that's saying is we can be 95% confident that the true mean of the values or of the data lies within 2.4, or lies within 60.88 and 65.68. Somewhere in there we're 95% sure that the true mean exists. And that's also, I kind of jumped ahead, that does also answer part C as well. We did find the confidence interval. Part B just wanted us to show that it does exist. So it's 2 times the standard deviation. That's all we're looking at part B. For part C, this is what we're asked to find, is this range 60.88 to 65.68. A lot of noise going on around here at the house today. The dogs running around, barking, wanting to go in and out. So I apologize for that. Some definitions we want to keep in mind. Confidence interval is just the interval of numbers obtained from a point estimate of a parameter. That's what we calculated in part C of example 2. The confidence level is the confidence that we have that the parameter lies within that given interval. So if you look back at example 2, we were 95% confident that the true mean lies within the 2 values that we ended up calculating. So this is just a rehash of example 2. Now we want to interpret a confidence interval. And example 3 is asking us to once again look at the prices of the mobile homes as we've done in examples 1 and 2. And we want to determine whether or not our confidence interval is fairly accurate. So what I've done is I've already generated 25 samples. I think on here it mentioned that I did 20, but I actually did 25 samples of 36 new mobile home prices. And in that simulation, I calculated the sample mean. Not the sample mean, but what I did was I took each one of those individual samples and I used that minus 2.4 and plus 2.4 on every one of the values to demonstrate a confidence interval for all 25 samples. And when I go over here and open this up, in the left-hand column I have the samples, and you can see I used a mean of 65. Now we did not know the population mean. I'm just assuming this for right now just to illustrate a point, because 65 did fall within our confidence interval that we found earlier. I just picked that number kind of arbitrarily just to see how this would work, or to demonstrate how this would work. And then we have our sample standard deviation of 1.2. So I did this simulation just like we've done before, using these values, a mean of 65, sample standard deviation of 1.2. And then I've generated these 25 confidence intervals. So each confidence interval that you see here, the lower bound is simply the sample value minus 2.4. The upper bound is the sample value plus 2.4. Now remember, we calculated that because our standard deviation was 1.2. A 95% confidence interval is 2 standard deviations from the mean. That's to the left and to the right. So that's why we do minus and plus. So here are my confidence intervals for every sample generated. And what I'm going to do is I'm just going to simply go through here and highlight every one of the samples that has 65 within that confidence interval. And I apologize for these dogs. They are really loud. All right, so these first 2 do contain the sample mean, or the population mean of 65. Just going to keep scrolling down until I hit any more that do not. Okay, 65.19 to 69.99 does not contain 65. Still scrolling down. And the remainder of them do contain 65. So what I have out of the 25 samples, 23 of the 25 do contain that sample or that population mean. So if we were to simplify that and look and see what we ended up with, we had 92% of our samples contain the population mean. And that was just off 25 samples. If we extended that out to 1,000 samples, there's a higher likelihood that we're going to get to the 95% that we predicted based off the information provided. I do believe that was the last example. Yeah. So here is a different sample that I ran earlier. These are the 20. That's what I was talking about when I typed in 20 up there. Here's my 20 samples. Here's my 95.4% confidence interval. And we're looking at whether or not the population mean is within that interval. All of these is yes, except for this one. So we actually ended up with 19 out of 20. And that is a 95% confidence interval that, or 95% of the values line up. And then here's a graphical representation here on the right. Sorry about that. I've highlighted the assumed population mean with this blue dotted line. And then we have all these values, these confidence intervals that show how they relate to the population mean. So you can see just this one right here is the only one out of these 20 that does not cross over this blue dotted line in some way. So that's the only value or the only confidence interval that does not contain the true population mean. We're going to build upon this a little bit more, but that was just kind of an introduction to confidence intervals, and I hope that was somewhat fairly easy to understand. Again, if you have questions, please just ask me.